This little video to help you with the review today. I know there's like 30 some questions on the review. Here there's only 6, but these are the same type of questions. And these are the hardest ones, so I'm going to help you out. All right, so a gas is kept constant at a constant temperature and its volume goes up from 6 to 18. What happens to the pressure? All right, so first we got to know the relationship between volume and pressure. So this container over here, if the volume goes down, you make the space inside here smaller. There's the same number of air particles or molecules, but now they're squished together. So now they're pressing or colliding against the sides of the container more often. That's going to cause the pressure to go up. So if the volume or space goes down, it gets smaller, the pressure is going to go up. But the question says the volume goes up. It goes from 6 liters to 18. So what's that going to do to the pressure? Now, these little air particles, they're more spread out. They're not going to be banging against the sides of the container as often. So that's going to cause the pressure to go down. But how much? So if volume goes up, pressure is going to go down. So the volume went from 6 to 18. Not real easy to draw with this. So it goes from 6 to 18. So how much more is 18 than 6? Well, you can do 18 divided by 6 if you want. 18 divided by 6 equals 3. Since it's an inverse relationship, if the volume goes up times 3, the pressure is going to be 1/3. So the pressure, I'll just put P for pressure, is going to equal 1/3. It's going to be 1/3 the pressure. When the volume went up times 3, the pressure is now going to be 1/3. If the volume went up to 12, went up by times 2, the pressure would be 1/2. All right, so that's number 1. All right, number 2, I'm going to use this same little container over here. This is pressure and temperature. Now, this is not an inverse relationship where if one goes up, the other goes down. This is if one goes up, the other goes up, and that's the same thing for temperature and volume. So both of those, if one goes up, the other one's going to go up by the same amount. All right, so here we go. The temperature increases from 200 to 800 Kelvin. What happens to the pressure inside the container? So it's basically the opposite of what we did the first time. So the temperature goes from 200 to 800 Kelvin. All right, so since it's in Kelvin, 200 to 800, what is that? To go from 200 to 800, that's times 4. So since the temperature increased by 4 times, the pressure, what's going to happen to the pressure? The pressure is also going to equal times 4. So the pressure, whatever it is, it doesn't say what the pressure was, but if it was 1 atmosphere, if the temperature increases times 4, the pressure is going to increase times 4, so it'd be 4 atmospheres. There's number 2. All right, so number 3, this is a combined gas law problem. So I wrote down the equation over here on the right, which will be provided for you. So it's just filling in variables. So zero point 0.8 atm, that's pressure 1 or P1. So I'm going to do that. 0.8 is our pressure 1, P1. Volume is 5 liters. 5 liters. So you got to know these units by now. Volume is in liters, pressure is in atmospheres or kilopascals, and 280, that is a temperature in Kelvin. So T1 is going to be 280 equals. All right, so now what do we got? Volume 2 is 2 liters. So I'm going to put 2 for V2. And it doesn't, we're trying to figure out what P2 is. So we want to figure out P. All right, and our T2 is 350 Kelvin. 350 Kelvin. All right, so what are we going to do here? Let me get my calculator. Should have had it ready, but I don't. All right, so I'm going to simplify the left side first. So I'm doing 0.8 times 5. So I'm doing the left side. 0.8 times 5 equals 4. Divided by 280. Divided by 280 equals. So the left side is. So I got the left side. Let's see if my little pen's going to work. And there we go. All right, so the left side is 0.014 equals 2p over 350. All right, so I'm going to write it over here now. So now I got to get rid of 350 on the bottom. So I'm going to multiply both sides by 350. So 0.14 times 350 equals, so now I got 5. All right, so 350 times this is 0.14 is going to be 5 equals, and I still have 2p on the left side. So to get P by itself, I'm going to divide both sides by 2. 5 divided by 2. So P is going to equal, let's see, 5 divided by 2 equals 2.5. I should have been able to do that in my head, but I didn't even think about it. So P equals 2.5. So our new pressure is 2.5 atmospheres. So that's how you do the combined gas law problems. All right, number 4. This is an ideal gas law problem. Let's see if my little pen's been working. Oh, no, I got it on eraser. All right, let me put it on drawing. Boink. All right, and here we go. All right, so we got our equation here. PV equals nRT, which will be provided for you. You got to know P equals pressure by now. V equals volume. N is the number of moles. R is the constant, which is right here, 0.0821, since our pressure is going to be in atmosphere. And temperature's got to be in Kelvin. So here we go. So we're just plugging in numbers. So we want to figure out how many moles of the gas. Moles is N. So remember, if you get these confused, since you're multiplying them all, it doesn't matter if you forget what N is. You just got to know that moles is over here, because like if moles was 3 and R is this, you got to know that. And temperature is 350. Since you're multiplying them all, it doesn't matter what order you put them in. You just got to know pressure and volumes on the left, moles, the constant, and temperature is going to be on the right. All right, so I'm just filling in variables. All right, so our pressure is 1.5. That's P. Our volume is 4. So I just got, it doesn't matter if it's 4 on the left over here and 1.5, because 1.5 times 4 is the same as 4.1.5. So we just need pressure and volume on the left equals, we're solving for a number of moles, N. Our constant is 0.082. I'm just going to put 2 to make it easier. And our temperature is, it's already in Kelvin, so we don't have to convert it from Celsius to Kelvin. It's 350. All right, so now since we did this, literally all I'm doing is using a calculator. I'm going to simplify both sides. So first I'm going to do 1.5 times 4. The left side, 1.5 times 4 equals, so we got 6 on the left side over here. 6 equals, simplify the right side. We're going to get, I'm going to go 0.082 times 350. 0.082 times 350 equals 28.7 N. And we're going to solve for N. So we got 28.7, because 0.082 times 350 is 28.7 N. Now to solve for N, I get N by itself. I got to divide both sides by 28.7. So I got to divide this side by 28.7. Now what's 6 divided by 28.7? It's going to give us the number of moles. 6 divided by 28.7 equals, we got 0.21 moles. So N equals 0.21. So that's moles. So that's how many moles of gas we got. We got about 0.2 moles. All right, that's number 4. All right, here is a specific heat problem. Number 5. Let's see if my, there we go. All right, so here's our equation. Q equals mc delta T. Q is energy in joules. M is the mass. M is always mass. C is the constant, or the specific heat, which is right here. The specific heat of aluminum is 0.9. So that is the specific heat of aluminum. Remember, it's different. Water is 4.18. The higher the number, the more energy it's going to take to heat that substance by 1 degree Celsius, 1 gram of it by 1 degree Celsius. And delta T means delta triangle. The triangle means change in temperature. T is always temperature, change in temperature. So we got everything we need here. All right, so we're solving for Q. How much heat did the aluminum absorb? All right, so Q is energy, heat energy. So M, what's M? It's right on the top. M is mass. It says it's 35 grams. We'll put 35. C is over here. Remember, C is the specific heat. And in this case, for aluminum, it is 0.9 joules per gram degree Celsius. And delta T, change in temperature. So the temperature went from 24 to 64. So it went up by, to figure it out, its final temperature, which is 64, minus the initial temperature of 24. 64 times 20, or minus 24 would be 40. So the temperature increased by 40 degrees Celsius. And remember, Celsius is fine with this one. You don't have to convert it. Fahrenheit's no good, but Celsius or Kelvin are fine. All right, so there we go. I set it up. So there's our mass. There's our specific heat of aluminum, and there's the change in temperature. It increased by 40, didn't decrease, went up. So it's a positive number. All right, so now the calculator. 35 times 0.9, 0.9 times 40 equals 1,260. So how much energy, how much heat energy did the aluminum absorb? It absorbed 1,260 joules of energy. And that's just straight up just putting in some numbers into the equation that's provided and then just using the calculator. All right, the last one, a little calorimetry problem. All right, so here we go. All right. So you're going to try to figure out what metal it is. So we're going to use this equation right here. We're going to start by figuring out how much energy in joules the water gained, because you put a hot piece of metal in water. Of course, the water is going to heat up because the heat goes from the metal, the hotter object, to the cooler object, the water. So the water is going to heat up. If we figure out how much the water heats up, since we know the specific heat of water right here, we'll be able to figure out how much energy the water absorbed from the metal. And then we can do another equation and figure out which metal it is. So we're using the same equation. It's right here. But first we're going to do water. How much energy did the water gain? So Q is energy in joules. M is the mass. We should know that by now. Mass of the water is 50. 50 times the specific heat of water, which is right here, 4.18. That's why we're using water, because we know its specific heat. If we knew the specific heat of the metal, we would just pick which metal it is, but we don't know it. So that's why we're doing the water first, because we know its specific heat. We can't put in one of these specific heats for these metals because we don't know which metal it is. So we figure out how much energy used in the water first, and then change in temperature. So the water started at 20.0 degrees Celsius, and at the end, the metal heated up to 32.4. So 32.4 minus 20 is going to be 12.4. So the water went up by 12.4 degrees Celsius. All right, let me put a little, oh wait, this is 50. All right, that's not 150. That's 50. All right, so now I just do this math. Let me get my calculator. All right, so this is how much energy the water absorbed from the metal. So it's 50 times the specific heat, 4.18, times 12.4. 12.4 equals 2,591.6. I'm just going to put, so the water increase in thermal energy or heat energy by 2,591 joules. That's how much energy the water absorbed. So that's the same amount of energy that the metal gave off, because remember, conservation of energy. Energy wasn't created here. It was just transferred. Heat energy was transferred from the hot metal to the colder water. So that's how much energy the metal had. So now we're going to do this same equation, but now we're going to try and solve not for Q, but we're going to try to solve for C. Because if we figure out the specific heat, it's going to be one of these numbers, and then we can figure out what metal it is. All right, so now we know Q is 2,591, because that's how much energy the metal had, because the water gained this much, so the metal had to have lost this much. The mass of the metal is literally given to us. It's 100 grams. Now, if you don't know grams is mass by now, just study that. It's not, we don't have that many units. The specific heat we don't know, so we're going to put C for that. The change in temperature we do know. It started at 100, and then both of them, the water and the metal, ended at 32.4. So let's see how much the metal, obviously it went down. So it's 100. So I'm going to go 100. This is going to give it to me a positive number, which is fine. It don't matter. I just need to know how much the temperature changed. So 100 minus 32.4 equals, I could have got a negative number, but I just need to know how much the temperature changed. And the temperature went down by 67.6 degrees Celsius. So that's all we need. So we got our mass, specific heat, we don't know, and the change in temperature was 67.6. So now on the left side, 100 times 67.6, I should be able to do this in my head. It's going to be, on the left side, it's going to be 6,760. C, don't forget C, we're solving for C, equals 2,591. Now to get C by itself, I'm going to divide both sides by 6,760. 6,760. And when we do that, 2591 divided by 6760. Oh, 6760 equals, I get 0.38. So C equals 0.38. And I will compare that number. 0.9, not very close. Oh, copper, 0.38. Ding, 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 ding. There is our mystery metal because we figured out the specific heat of this metal was 0.38. So there's your metal because it has the same specific heat. Iron, a little too much. Lead, not enough. All right, so there you go. Do your best. We will have an exam, it looks like, on Friday. So email me with any questions. I will be at school on Friday. Feel free to come in at lunch.